In this video, I'm gonna talk about how to solve non-homogeneous differential equation with constant coefficients using the method of variation of parameters. Given y double prime plus y equal to 1 over 1 plus sine x, find the general solution. The first thing that we are going to do to find the general solution of this equation is to solve for the complementary or auxiliary solution yc, and use that to solve for our particular solution yp. So how do we do that? First, we will solve the homogeneous part of this equation. And by saying that homogeneous, it means that the equation must be equated to zero as shown. Here, we use variable m to represent the unknown in the equation, and thus m is equal to the square root of -1 or plus minus I. Notice that this is case 3, with a complex conjugate roots, positive I and negative I. If the nature of the root is of the form alpha plus minus beta I, the corresponding auxiliary solution would be y equal to e to the alpha x. This term multiplied by c1 cosine beta x plus c2 sine beta x. In this case, we have 0 as our alpha, and e to the 0 is just equal to 1. So we are left with yc equal to c1 cosine x plus c2 sine x. Now that we have our auxiliary solution, we will next solve for yp using variation of parameters. The formula for our yp is u1 y1 plus u2 y2, where y1 and y2 are cosine x and sine x respectively. This cosine x and sine x, by the way, is taken from our yc, with the first term cosine x referring to y1 and the second term to y2. So now, our yp would be equal to u1 cosine x plus u2 sine x. Since we already have our equation for yp, the next step would be to find the unknowns u1 and u2. Formula for u1 is the integral of w1 divided by w, and u2 is the integral of w2 divided by w. W is the determinant of these terms. Our first column, first row, corresponds to y1, and second row, y1 prime. Second column, first row, y2, second row, second column, y2 prime. Anyways, it doesn't necessarily mean that we stop at y2. The terms inside the determinant sign depends on the number of terms of yp. If yp has a third term, y3, then we also write y3 inside the determinant. For our w1, we substitute the first column. Instead of writing y1 and y1 prime, we change it to 0 and f of x. As you remembered, this is what we call your Cramer's rule. Same thing goes for w2. The only difference is that we now substitute 0 and f of x on the second column, leaving the first column as it is in the original. F of x, by the way, corresponds to the right side of your original equation. In this case, we have 1 over 1 plus sine x. Given the significant formulas, what we just have to do is simply substitute the terms and perform the necessary operations. So we now have w equal to 1, w1 equal to the negative of sine x all over 1 plus sine x, and w2 equal to cosine x all over 1 plus sine x. With values for w, W1 and W2 known, we find U1 and U2. For U1, U1 is equal to the integral of W1 over W. Substituting the terms, we have the integral of negative sine x all over 1 plus sine x. By inspection of the integrand, it would be difficult for us to integrate it manually and directly. And so, what we are going to do is we introduce a term to be multiplied both to the numerator and denominator, such that the whole term would be integrable. In this case, we choose the conjugate of 1 plus sine x, which is 1 minus sine x. So now we have the negative of the quantity sine x minus sine squared x all over 1 minus sine squared x. Note that 1 minus sine squared x could also be written as cosine squared x. And so we have the negative of the quantity sine x minus sine squared x all over cosine squared x. The next step to do is to separate this whole term into two terms. And so we have the negative of sine x over cosine squared x plus sine squared x over cosine squared x. The denominator of the first term, cosine squared x, can be written as cosine x times another cosine x. Using our knowledge of the basic trigonometric identities, we write this term into negative tangent x second x, since sine x over cosine x is equal to tangent x, and 1 over cosine x equal to second of x. The second term, sine squared x over cosine squared x, is just equal to tangent squared of x. Now that we already transformed u1 prime into something that is integrable, we now integrate it. So we have our u1 equal to sine x minus 1 over cosine x, this term minus x plus some constant c1. We are done now of u1, so next we will find u2. Given the equation for u2 equal to the integral of w2 over w, substituting gives the integral of cosine x over 1 plus sine x dx. We let u equal to 1 plus sine x, and so du would be equal to cosine x dx. Now we substitute u and du into our equation. And so, we now have the integral of du over u, which is equal to ln of u plus some constant c2. Substituting back the value for u, we have u2 equal to ln of 1 plus sine x plus some constant c2. Recall that our yp is equal to u1 cosine x plus u2 sine x. Since we now have the exact terms for u1 and u2, we now substitute them into the equation. Simplifying the terms, our yp is equal to sine x minus 1 minus x cosine of x plus sine x multiplied by the ln of 1 plus sine x. Also, note that our aim here is to find for the general solution for the differential equation. The formula for y is equal to yc plus yp. Replacing these terms with the exact terms will give us y equal to c1 cosine x plus c2 sine x plus sine x minus 1 minus x cosine of x plus sine x multiplied by ln of 1 plus sine x. This is now our general solution. Thank you for listening and hope you enjoy watching this video.